Thank you, Emil. Hi, everyone. Thanks for coming back today. I hope you enjoyed our first two sessions. Um, let's first of all see if you have any questions from yesterday. I'll share my screen in the meantime. So yeah, please feel free to unmute yourself and speak up or put your questions in the chat. Let's make sure that everything was clear from the first two sessions before we move on to the new stuff that we are going to discuss today. Okay, so if there's no questions from yesterday, um, let's talk about some more options of YARA today. Just a reminder from yesterday, we talked about Uh, last thing we talked about was the strings, the kind of strings that we look for in a file when we are trying to write an effective YARA rule to catch similar files. These are the types of strings that we are interested in and might be unique by themselves or in different combinations with different conditions, they might be quite effective in catching similar samples and avoiding false positives, of course. So today we are going to talk about some more options for conditions and then move on to talking about different modules from YARA, um, like extended modules like P module, time, math, these modules that can be included into a YARA rule and can be helpful in defining different conditions and extracting different information about the P file. So first of all, talking about the conditions, this is the extended version of the basic conditions that we have seen so far. Let me talk about some of these. The first one, we have tried this before. This means that the string A needs to be at offset 0. Second one, a string A at p dot entry point. So this is basically an information that is extracted by P module of YARA. You need to first include that module into your YARA rule with the keyword import, which we'll see later. And then this field here, entry point, shows the address of the entry point of the P file, which is the first line of code instruction in the compiled file. And we want, with this line, we basically wanted some specific hexadecimal sequence of bytes to be at the entry point of the file, which makes sense in cases of different malwares and different files, as some developers have their own method of writing the code, or sometimes the file might be packed and the specific packer might have a special um, routine at the beginning of the code. Next one, string A at sign B plus 16. What this means is that with the at symbol, we get access to the offset that the string B was found in the file. And with this line, we want the string A to be where a string B was found plus 16. So basically the two strings A and B, we want them to be 16 bytes away from each other, and we want the string A to be present after string B. This one, string A, in 0 to 100. This is a range of offsets. So the string A, we want to be from somewhere from offset 0 to offset 100. And then we want the string B to be there in the offset 100 up until the end of the file, which is shown by file size. So again, with this one, we want the two strings to be present at the file in the file, but we want the string A to be at the first 100 bytes of the file and the string B somewhere after that. Next one, a string A in p.entry point until and the range of p.entry point to p.entry point plus 10. So it's clear what this means. It means that we want the string A to be somewhere in the first 10 bytes of the instructions that are going to be executed in the code. This one, two of A, B, and C. This means that we want a subset of two of these three strings to be present. Of course, if three of them are present, it still works because this is the minimum condition that we want the file to have. We can also use two of them. Them means all the strings that are defined in the string section, whether they have similar like name prefixes or not. Um, it is it means every string in the string section. Two of $A star. And this is very useful when you want to categorize some strings. Like for example, you have a number of strings that you want some of these strings to be present in the file, and you have another category of strings and you want some other specific number of these strings to be at the file as well. So we define the name of the strings with different prefixes like A1, A2, A3, and then the other category could be B1, B2, B3, B4. And with a condition like this, we specify that we want two of the strings that start with A to be present at the file. All of them, again, means all the strings in the string section. Any of them means at least one of them, one of the strings. A and not B, which is clear. We want the string A to be there, and we don't want the string B to be in the file. So this is about the extended version of the conditions. We are going to move to additional YARA modules. If there is no questions, let me see how I can see the chat. Okay, so I guess there is no questions. So let's talk about the additional YARA modules. First of all, let's talk about the PE file format. I'm not sure how many of you are familiar with the PE file format, but PE is the or portable executable is the format used by typical Windows executable files, libraries, and drivers. These are files that are supported in different versions of Windows operating system from x32, x64, ARM platforms. These files usually, the P files usually have can have different extensions from .exe, .dll, .scr, .cpl, .ocx, and some of the .sys files, which are the drivers of operating system that work in the kernel mode, are in this file format. If you want to learn more about the P format, which is actually very useful if you are dealing with malware files and you are trying to write YARA rules to find new malwares or to detect different malware families, it's very important to have a good understanding of the P file format. In general, a PE file consists of headers and sections. Headers are are there to describe how to load the P file in memory and how to execute it. And also sections contain code, data, and different essential P structures that we will see a little bit later. Also, categorizing P files by CPU, we have P for 32-bit platforms and P plus for 64-bit platforms. This is this chart that you see here, like this diagram. It shows a common P file with the headers at the bottom, which is the lower offsets starting from 0, offset 0, for each file, and goes towards higher offsets with the P header section table that defines different characteristics of different sections. For example, where each section is at on the disk, what is the size of each section on the disk, how it will be mapped in memory, where it will be mapped, and what's the size for a mapped section in memory, and some characteristics about the section, like if it's executable, if there's executable code inside the section, if it's only writable or readable, and so on. Then we have different sections, and these sections, in most cases, they have common names, like what you see here, .text, .data, other sections, .relog. These section names are quite common among files that are compiled with Visual Studio. And we have other common section names for files that are compiled with other compilers, and also packed files. In most cases, they have common section names for themselves, but it's quite common to see sections with unusual names in different files, especially in packed files or in malware files, which in that case, it's a very good opportunity to use that section name in a YARA rule and make sure that this is um, put in the condition to find files with similar section name. Also, as you see here, the P file in on disk and P file in memory might be a little bit different, and this is due to the definition of the section table. As I explained, different sections can be mapped into memory with like different sizes and different offsets, relative offsets to the beginning of the file, compared to how they are present on disk. Talking a little bit about the headers. First of all, at the beginning of the PE file, as you see in the offset 0, we have the DOS header, and then we have the PE header. There are two important magic strings in a PE file. The first one at the offset 0, we have 4D5A. If you remember from the YARA rules that we have seen so far, we had the uint 16 at offset 0, 0x5A 4D, which shows the MZ. This is MZ is the ASCII representation of these 2 bytes, of the first 2 bytes. And this is the magic header of a PE file. Also, there's another magic value, which is the PE. That is the start of another header in the executable file, which is the PE file. Why we don't use this magic value in YARA rules? The reason is that the offset is not always consistent in the offset of the PE. Magic value is not always consistent in the file, but there is a specific and constant offset in the DOS header that has the address to the PE header, which is the offset 3C. If you notice here at 3C, we have E8, and at E8, we have the PE. but this is not easy to define in a YARA rule, so it's much easier to use MZ. Sometimes in some malwares, the module that loads another module of the attack um, modifies these headers, and because they load the malware themselves and they don't rely on the Windows loader, it's okay if they change some headers because they would still know how to load it. In those cases, if they use specific uh, string or specific hex values instead of the MZ, like standard MZ, we can use that for unique characteristic in the YARA rule, or we can just rely on something else. Okay, moving on. This is a screenshot from a tool that I've shared with you, AdLice P Viewer. It's the free version that I shared with you, but you can also use the paid version, or you can use any other PE viewer that help extract different information from the PE headers. This is just one example. There are lots of other examples. And there's another one that I shared with you, which is the CFF Explorer. Both of these tools are only for Windows operating system. Um, but there are other tools that you can use on other operating systems. Of course, they are not as convenient and as like easy to use and easy to understand as the ones that are compiled and prepared for Windows operating system, because after all, we are looking at Windows files, like Windows executable files, and it makes sense to have a Windows system, at least a Windows virtual machine, to work with Windows executable files much easier. That's what I do and most other researchers do. Even if we use a Linux or Mac OS as our host machine, we usually have different Windows VMs, like different versions of Windows on different VMs to use different tools and make the analysis much easier, and also sometimes maybe run the malware to see how it works on the system without the risk of getting our own systems infected. So with this one, you can see that at the top, you can see different tabs that this tool has. It collects different information, extracts actually different information from the file, and puts them in different categories. Some of the information that you see in these tabs might be um, overlapping with each other. Um, but this is only because the tool wants to have like relevant information next to each other at different tabs. So we have the tab general that has like general information about the file, like what is the file format, maybe what's the hash, MD5 hash of the file, SHA-1 hash, SHA-256, and so on. What's the file size? And then we have other tabs. In the P header tab, there are lots of important and useful information for us. For example, you can see here that there is in the file header section, we have the machine which shows some value that means this is AMD x64 file. Then we have the timestamp, which is in Linux form, but there are calculators, converters actually online that you can use to convert that timestamp to human readable timestamp. We are going to actually use one of them later in an exercise. We have some other information. We have the characteristics details here, which shows if the file is executable, if it's a DLL, if it's 32-bit, if it's system file like a driver, sys file. Also at the bottom, we can see if it's a .NET assembly file, if it's a 64-bit file, and so on. Also in optional header, which is another header in the file, It's not actually optional. It's a mandatory header in P headers. And don't be confused with the name optional header. It's always present in a P header, but there are some parts that are actually optional. They are present in some files and are missing in some other files based on the structure and logic of the file. And I'll explain it in a minute. So optional header starts with some information that you see at the top. We have the linker version, we have the size of initialized data, we have the base of the code, the entry point, which we already talked about a little bit. This is the address of the entry point. Um, Also some other information. Um, we have size of the code, size of image, um, some other information, and after the first part of the optional header ends, we have some very important structures for a P file, which are called data directories. These data directories are things like import directory, resource directory, exception directory, export directory, and so on. And these are actually the optional parts. Like, for example, you don't see export directory in a lot of executable files. Export directory is very common with DLLs, which are dynamic link libraries. You don't see them a lot in standalone executable files. Or debug directory might not have any content in a file. Um, so moving on, talking about different sections of the PE. The PE header, as I said, comes after the optional header. Um, so every section in the file has a structure, has object inside the inside the section table. Um, that structure has different information about the section. You have the name, which is 8-byte section name. Um, as I explained already, there are standard names for sections like .text or code for code section, the .rs/rc for resource section, and etc. But true section content type is defined by characteristics field. Also, for each section, we have the virtual address and virtual size, which shows the offset of the section in memory. These are in memory section parameters, show where to load section content. In fact, true size of section in memory is virtual size aligned up to section alignment from PE header. So what this means is that the physical size of each section is usually quite similar to the size in on disk, but in memory it has to be aligned with the page size of the memory. That's why it might be different. We will look at an example here in a minute. So we have characteristics, which are section properties flags, which tell the loader if section is readable, writable, executable. Main flags are here. You can see the execute, read, and write with their values, and they can be combined with each other to make a section executable and readable and writable and so on. So an example here, a typical Delphi program section table in Hue, which is a PE viewer, also common for Windows operating system, very powerful and very useful. We have virtual size, or we have virtual size and RVA, which are virtual size and relative virtual address in memory. We have physical size and offset, which are size of raw data and pointer to raw data on disk. We have flags, which are characteristics. And the third section is empty here, as you see, the BSS section, the section that is named BSS, has 0 physical size. So if you notice here, in many cases, the virtual size and physical size are just a little bit different. And that's because the physical size is aligned with the page size on disk. Uh, so talking about the PE data directories a little bit, I talked about the export directory earlier, but again, this is an important part of DLLs, which describes how and what functions does a library export and what their addresses are. So these exported functions are going to be used by other programs to interact with this DLL. Also, we have import directory. What is import directory? Each program needs to interact with the operating system and other components, and import directory describes which functions from what libraries does the program require. And during the loading process in Windows operating system, the loader searches libraries from the import directory in the system and fills import function table in the program image. The program uses this table later for external function calls. So basically, the loader looks at the import directory and checks which libraries and which functions from these libraries are required by this program, and then loads that libraries off, or if they are already loaded in some cases, in some circumstances, it just uses the same address to fill the import table, and then the program can use them later to interact with the operating system and with other components. Also, we have relocation directory. So in many cases, PE images usually contain absolute virtual addresses. And these absolute virtual addresses are not fixed in the file. When the base address of the program changes, like for example, when the file is loaded in a different image base, these relative absolute addresses are not going to work anymore. So the relocation table contains info for the loader to fix these parts and use and adjust it to the new image base. Also, another important data directory is the resource directory, which contains all the program resources like the strings, dialogues, menu descriptions, version information, manifest icons, and so on. And in many cases with malwares, you see another malware module inside the resource entry. And when you try to do reverse engineering and look at the code itself, you can see that at some point the malware reaches out to that resource entry of itself, loads it, and drops it somewhere on the system, or just loads it in memory and makes use of that option of having a resource entry. Um, so I'm sure there was a lot of information to take in a few minutes, but that was just because I wanted to give you some idea about the PE file format and lots of other information that are present in the headers of a PE file and can be used to write an effective YARA rule that finds a file not only based on the strings inside the file, but only but also based on different characteristics of the P file and different like more like metadata information. So there is a P module that is written for YARA and can be used in a YARA rule. And this P module actually extracts a lot of the information that we have just discussed about from the P headers, from different sections, from section table, and so on. To use the P module, you need to add the line import P in double quotation at the beginning of your YARA rule. In most cases, it is already installed. I mean, it's already included in the YARA engine that you have installed on your system. But in some cases, like in some Linux versions, it might not be there. So in that case, you need to download the code from, it's a open source code. You need to download it and compile it yourself and add it to your engine. But I'm sure most of you, if you try, already have it with your engine. So talking about some of the use cases that we can use the P module. For example, here you can see that we can use P.characteristics with the logical and P.dll to make sure that we are only catching DLL files and not um, any other P format. Also here, p.exports, this name, what this means is that we want the P file to have an export function with this name splsa mode initialize. P.imports, you can use it like this. You can use the DLL name and the function name, like procedure name. So this means that you want the file to have write process memory function from kernel32.dll imported in its import table. Also pe.machine, we want this to be pe.machine underline AMD64. This is another example. Also, you can use the p.timestamp to have a specific time. You can use this website that I put here, epoch converter, or any other time converter, online time converter that you find to convert this time to um, normal human readable time, or vice versa. Like for example, we have an exercise later that I want you to find files that are compiled after a specific time. So in that case, you need to convert that time to the Linux format of time and then check the p timestamp to that value. That was a hint that I already gave you. So another set of information, useful information for P module, you can use the P local or P language that can show the language information, that can use the language information used in the file. This could be from resource entries and left in the file because of the compiler being used on a system with a specific language, or the compiler itself might be a specific version for like some language, and these values are left inside the code inside some of the resource entries and can be used for our benefit in the YARA rules to make sure that we are catching files that are written and compiled on for example, Russian operating system or a Chinese operating system, um, or an English version of operating system. Also here, we can use the version information of the file, which is very useful in many cases. Um, Here, this is an example to check the company name in the version information to have the string Adobe inside it. Another one is the p.imp hash. What is imp hash? Imp hash or import hash is a specific hash of, it's actually an MD5 hash that is calculated from the import table of the file with after doing some normalization. So basically, different files that have similar import functions have the same import hash. This is also very useful in finding similar malwares in different cases. Then here we are looking at p.sections with the index of p.section index.payload. What this means is that we know that there is a section that is named .payload. We want to get the index of that section and then use that index to look for the raw data offset inside the section table. Also, we have p.sections, index4.name. We want it to be .payload. So it might be the same section, payload section that we were trying to get access to the raw data offset of it in the previous line. Um, Also, another very um, useful thing in the P module is its ability to extract the digital signatures. Like here, we are trying to see if the first digital signature that was found in the file has this specific serial number. Let's see if you guys have any questions, and then we can move on to our first exercise for today. I see something in the chat, but I don't know what's going on. So no questions, everything was clear. Okay, great. So let's work on this exercise. If you remember the YARA rule that we have written yesterday for the module that was from the .NET Visual Studio .NET environment, I want you to look at that YARA rule and try to improve it with the help of the PE module to make it more accurate. I mean, not just looking for the Visual Studio .NET string inside the file, but to make sure that this is not just a string in the file, it has a meaning um, um, where this string is used. And also there is something specific about .NET modules in their import table, import directory. I want you to find out what that is and add that unique characteristic of the .NET modules inside your YARA rule. So for this, you need to try using one of the tools that I've provided, either the AdLice Viewer or the CFF Explorer, or if you have any other Viewer tool that you are comfortable with, um, it's the same. You can use it. I actually um, have a habit of using an internal utility of Linux to look at some P headers. It might not be as nice and like easy to work with as compared to, for example, Atlas or CFF, but it saves me time to not to open a VM every time I want to look at some P headers and um, open up that tool and look at that file and come back to my host machine. So whatever you're comfortable with, you can try and find this information and add to your YARA rule. I guess it should be 6:15, almost 6:15 in Singapore. So I guess maybe let's give it 10 minutes first and see how we go, and let me know if you have any questions or if something is not clear, or definitely let me know if you proceeded to find something and you have been successful in finding something that's useful. Okay, so JH is asking what is the Linux tool to examine P files. The tool that I'm using is object dump. It's not very, it's an old tool, but it can definitely be used with dash um, with dash X. Let me show you how to do it. You can get the headers of the file. It's best when used with Linux compiled files, but it can work with most of the Windows executable files as well, and it can extract lots of information from it. So feel free to use. So just to give you some direction and not to get confused, please first of all try to, of course, first of all find your YARA rule from yesterday. This was related to the exercise 2 file. You can even check it again today, extracting the strings and looking at the a string that shows it belongs to the .NET environment. But then start with trying to see and find different information from the PE header. Use either CFF Explorer or Atlas, or if you have any favorite PE viewer tool, just use that one and try to find some information from the headers. Guys, I'll put the address to the YARA P module documentation in the chat, so you can have a look and see what parts, what fields you want to use and what is useful for you and what's the syntax. Okay, if no one has found anything useful yet, let me show you how to see different information from the P header in Atlas and CFF Explorer. And if you want, I can also show you the Linux tool that I use to look at the P headers. Let me start sharing my other screen. So this is a Windows VM. Um, this is the exercise 2 file that we want to have a look. So I have the Atlas P viewer here, which at the first time you need to accept some agreement, and then you can just drag your file here and have a look at different information inside the file. I hope it's not too small. Can someone just confirm that you can see what I'm showing in the it's okay. Okay, perfect. So as you see, we have some information about this file here. You can also see here that we have some product information that shows Microsoft Visual Studio.net. We have the version. We have some other information here. Also, there's a tab, image tab. It actually shows an image based on the file content. It's useful if you want to look at the entropy and anomalies in the file. And basically, you can see some parts that are less dense, that parts are have like lower entropies, and the parts that are denser in the image have higher entropy. Um, we don't want to deal with this now, but you have also other tabs here. What is interesting for us is the PE header that we actually saw in a screenshot in the slides as well. Here we have some information about the timestamp. You can see that timestamp is converted here for us, which is 12th of December 2002. There are some other information. You can see that this file is executable. It's a DLL, and there are no symbols inside the code. They were stripped from the code. This is a .NET assembly. It's a 32-bit file, and we have some other information here. We have the data directories here. You can see for each data directory, if you click on it, um, it it is highlighted. You can see the virtual address. You can see in which section this data directory is found, and also you can see the size. Moving to the P section here, you can see that there are 3 sections in this file, and for each section you have the virtual size, virtual address, physical size, offset to row data, which is the physical offset of the file. You have the flags and some other information like the entropy and ratio These are not actually extracted from the section header itself, but these are extra information that are calculated by this P viewer to help you with your analysis. We will, for example, talk about entropy um, later today and see how it can be useful in some cases to find like similar or similar malwares or malwares with the same characteristics. Uh, let's move on to the P imports. You can see here that there is one import DLL and one import function here. Also in the P debug, there is nothing. As I said previously, we have some files we can that we can find the PDB path inside. For example, the other file that we were working on, the exercise 3 file, but with this one, there's no PDB information and debug information left in the file. Also, the P resources we have here. You can see the resources and some information about them. This is the language code, like what I shared earlier. Um, these are information that are left inside the resource entries and help to figure out if the file was compiled on a system with a different language from English. Also, last but not least, we have version information and digital signatures information here with different fields like file version. What else do we have here? File type, file OS. We have product version, which is the version number. We have company name, which in this case is Microsoft Corporation. We have legal copyright and product name. Microsoft Visual Studio.net. This is actually the file and the string that we found yesterday to add to our YARA rule. And because of this special character here, we had these two parts of the string separated in our strings view. So we only saw the Visual Studio.net. So what we want here with the hints that I provided in the exercise, we want to add um, two characteristics of the .NET modules in our YARA rule. First of all, we want to make sure that the product name has the Visual Studio.net string inside it. And also another specific that I mentioned in the hints is that the Microsoft Visual Studio.NET modules, they all have only one import DLL commonly, majority of them, and that imported DLL is msquery.dll. And depending on if the file is a DLL module or if it's an executable module, there's only one specific function that is used and imported from msquery.dll. And with the .NET module that we have here, which is a DLL module, that only function is called _core DLL main. So if this is clear, let's write the YARA rule together. Or do you guys want to have some time to write your YARA rule, to write the YARA rule yourself? Let me know. I can also show you the same file in the other tool that I provided, the CFF Explorer. This is the same file. As you see, the GUI is completely different from the other tool, but nevertheless, the information that is extracted from the file is the same. You can see that the header information are here. You have file header like for example, the machine information, the timestamp is also here, characteristics. You have optional header, data directories. You have information about different data directories here, and also the import directory is extracted in a separate view. Here you can see that there is this one DLL, and when you click on it, you can see the functions that are imported. Also the resource directory, relocation directory, and with this specific file, because it's a .NET module, you can see some information extracted about the .NET directory present in the file as well. Also similar to Atlas, we have a resource editor here, which you can actually see the resources. You can copy them on this and work with them one by one. We have the hex editor that you can use to see the hexadecimal representation of the file content. Uh, that was it. Let's see if we can use that information in a YARA rule. I'm not sure if you guys still see this screen. Can you see my files? I can, or you still see the VM window? Okay, the files, great. Okay, so while we are here, let me actually show you the tool that I use on Linux, which is the object dump with -x option, exercise 2. You have all the information extracted from header. If you notice here at the end, we have the section information, the name of the section, size, virtual address, and so on. If we move up, we can see the resource directory. Also, we can see the import table here, which is the DLL name, msquery.dll, and also the function name that is imported here. Other information also extracted, like for example, the timestamp. In this case, you can see that it shows the timestamp in the like human readable timestamp, which is quite helpful when you want to look at this shortly and you don't want to spend a lot of time converting and looking at different tools. So talking about the YARA rule, let's write a new .NET YARA rule. Let's start with the name of the YARA rule, rule new .NET. Oops, I forgot to import the P module. Now here, let's forget about the meta section now. And also we don't want to use any strings. This is one of those examples that I mentioned yesterday, that sometimes you may not need the strings at all. You only need condition. And with condition, first of all, let's use uint 16 0 equals 0x5a4d. And okay, here we want to use the product name. So pe dot version. Let's make sure that we are doing it right. Let's look at the YARA PE module. So the syntax for version information is something like this. Let's actually copy this and put it here and change this to, we want the version info, the product name to contain Visual Studio .NET. I hope this is correct. And one more thing that we wanted to add is the imports. We use mscore.dll, and the function name was, what was the function name? Dump -x exercise 2. The function name was this. Let's go back here. Okay. And that's it. Let's see if it works. YARA-R new.NET. Okay, something is, oh yeah, sorry. This is it. No, what is it? Oops, it's this one. Oops. Sorry, give me a second. Let me focus on this and see what is wrong here. Okay. Sorry for the typos. Okay, now you see that we have catched the same 4 files from yesterday. So basically, in this case, our YARA rule is more specific. We don't only look for the string Visual Studio.NET, but we are actually specifying that this string should be in the product name, in the version information. And also we have the file header here. And also we want this to be inside the p imports. We can actually add another condition here to mention that we only want this specific DLL and function to be in the import functions and nothing else. In this case, we can add another option. We can add another condition here, PE. Let's see here, this is the number of imports. PE number of imports equals 1. And this should also work. Yep. Okay. Any questions? Was it clear? Okay, please let me know if this was clear, or if you have any questions. Let's answer them before moving to the next exercise. We have another exercise after this. Is the p dot imports operators case sensitive? I guess it is case sensitive, yes. Oh, actually you can see here that it says DLL name is case insensitive, sorry. No, it's not case sensitive. Okay, so basically how you are supposed to work with different modules is that before you get really used to different options and different fields and different functions from them, it's very useful to have the manual and documentation ready to make sure that you are using the latest syntax and you are using everything correct and you are making use of all the possibilities that that a specific module gives you. For example, there is the entry point field in the P module which was one word entry point that is changed um, for it's been changed for some time, and some old YARA rules are still using that keyword, but the new keyword is entry underscore point. So it's useful if you check the documentation from time to time, make sure that you are using the right syntax, and of course you are using the latest version of the module. Another question here, is it possible to show the rule again? Of course. So this is the rule. Any more questions? Should we move on to next exercise? Okay, so next exercise, stop sharing this screen. Let's come back to the slides here. So next exercise, we want to write a YARA rule to find files that are compiled between the year 2000 and 2010. And there should be 5 files in total. You can use this website, epochconverter.com, convert the timestamp, or any other online or offline time converter that you have. This should be easier. I guess maybe 10 minutes should be enough. Just a hint, guys, for this exercise, you don't need to actually look at any files. It's just the condition that you need to prepare and add to a YARA rule. So it's not YARA specific to any of the files in the collection or any of the exercise files. Just make sure that you prepare the condition in a way that finds and catches files that were compiled between 2000 and 2010. Has anyone managed to write the rule? Any idea how to do it? If it's not clear, let me know. Okay, I guess it's better if we do it together. So let me share that screen. So what we want to do is to find the time stamp of the first day of 2000, the year 2000, and the last day of 2010, and make sure that that the timestamp of the file is between these two timestamps, right? Should not be very difficult. Let's try to go to this, go to the link that I had put on the slide here. Okay, so here, let's change this to 2000, month 1, day 1, This is 0, 0, 0. Because this should be 12 a.m. Human date to timestamp. So this is the time, the first timestamp that we want. So let's create a YARA rule. Timestamp dot YARA rule timestamp. Again, let's only write the condition. Condition. Oops. Again, forgot to add to import the PE module. Okay, we want the PE dot timestamp to be bigger than this, and PE dot timestamp to be lower than 2010 12 day 30, this one. So this is the timestamp. Let's make sure this is correct. Okay, and that's it. So we have found 5 files where the timestamp was between 2000 and 2010. If we look at them one by one, we can confirm that the timestamp was between 2000 and 2010. Like for this one, let me just try object dump and grep it to time date. You see here, it was compiled in 2002. Let's try another one. You can in fact use the AdLice or CFF Explorer to find the timestamp. I'm just using this one to make it easier. This is also compiled the same date. As you see, just a few seconds after the first one. This one also. This is also compiled around the same time, just 1 minute later, and so on. Any questions? Okay, I hope the content today was not very confusing. I see no one is, I'm not sure if you are trying to do the exercises or you are tired and don't want to spend time on doing the exercises. But yeah, anyway, I hope it's not very, it's not too difficult. So we have a question, why can't use, yeah, we can actually use equal and greater than, or equal and lower than. Yeah, it's just, we can do that, of course. It's not very different. Basically, the files that we have here are not compiled at the exact first minute of 2000, the year 2000, or last minute of 2010. But yeah, thanks for mentioning it, Frankie. If you want to be more specific, we need to do that. Yes. Back to the rule. Okay. Did I stop sharing? Let me share the screen again and show you the rule. So this is the rule, quite easy. I didn't even check the P header, the MZ header. We can add that one too. Frankie, what was the syntax error you received? Oh, just a syntax error. Mm, can you double check your rule to see if you have not missed anything, like you have the colon here? You might have the line number where the error has occurred. Okay. Um, I don't know, to be honest. Maybe. It should work fine. Maybe you have used it. Mm, okay. Sorry, don't know what the problem was. Okay, let's move on. We have little more content to cover today. So let's talk about a few more modules, YARA modules other than P module. This one, the hash module, is also quite useful in some cases. If you remember, I talked about the import hash, which was the hash of the import section after some normalization that is done. Um, with that one, we need to calculate the hash in a way and compare it to the import hash of the file that we have. So we need some help to calculate the hash. And the YARA hash module helps us with generating MD5 values, SHA-256, SHA-1 values, and you can give it the address, the start address, and the size of the bytes that you want to calculate the hash for. As you see here in this screen, what we are doing here, for any I in 0 to p dot number of sections minus 1, hash.md5 p dot sections I dot raw data offset. And this is the offset of each section, and the size is p dot section index I dot raw data size, and this is the size, and we are comparing it with some constant value that we are interested in. So basically what we want here is to check for at least one section that has the same hash. Also, the next one, for any I in 0 to p dot number of resources minus 1, these are the different resource entries that are found in resource directory of the file. We want the SHA-256 hash value of that resource entry with the offset and length to be equal to this. So this is how you can use the hash module. Another module that could be useful is the math module. What this does, it can actually help with checking the entropy. I'll talk about entropy a little bit here. So basically, entropy is entropy shows the variation of bytes in the sequence that they are present in the file. What that means is that if the next byte is more predictable, the entropy is lower. So basically, if you have a constant value in a section, like you have a section that is filled with 0, the entropy should be very low. If you have sections that contain, or like parts of the file that contain strings, it is also a low entropy section, because like ASCII strings, the characters are only a small set of characters, and it makes it quite predictable to find the next byte. But if you have code in a section, compiled code, the entropy is higher. Still not very high, but if you have an encrypted section or a compressed section, the entropy is quite high. Also with packed files, the entropy of packed sections is quite high. So what you see here, two functions of the math module is used. The first one is math.inRange. InRange receives three parameters. The first one is the value that we want to check. The second one is the lower bound, and the third one is the upper bound of the range that we want to check if that value is in this range. And the next function that is used is the entropy function, math.entropy. This one receives two values, two import arguments. The first one is the index of the start of the data, and the next one is the size. As you see here, what we are trying to do is to check that the resource section with the name RSRC, we are trying to find the index of a section with the name RSRC and check the entropy of the whole section, which starts from the raw data offset until the raw data size. Of course, until the data offset plus size. We are trying to calculate the entropy of this section and check if it is between 6.66 and 8, which shows that this section is either compressed or packed or has encrypted data. Next module is the time module. Time is quite minimal. There's only like one function in the time module, and that is the function now. And this shows the time, the current time of the system. And it is compiled in the this means that the file is compiled in the future because the p timestamp is greater than time.now, which is an anomaly. It's something quite unusual to see the timestamp of a file being in the future, but it's common in some malwares that try to change and manipulate the headers to bypass some detections. So if you see something like that, this means that this is a suspicious file. Also, the second one, we are checking if the p timestamp is greater than time.now minus 86,400 and is less than time.now. What this means is that the file is compiled in the last 24 hours. These are quite useful if you run these sort of rules in a collection, for example, in VirusTotal or somewhere else, to make sure that you catch very new files that have been compiled in the past 24 hours. So another exercise, write a URL to find files with at least one high entropy section, entropy greater than 7. I'm not sure if we have time for the exercise. We can actually do it together to make sure that um, we are not going to run out of time. And the result actually would be 0 files in the collection. We have no files in the collection with the section that has high entropy over 7. But there is one file in the tools directory that I shared with you that has entropy greater than 7. And that's an installer file which has all the resources to be installed on the system encrypted and compressed inside the resource entry. So let's try to do it together. Okay, let's go directly to writing high entropy. Let's start with importing import math, also import P because we are trying to look at P sections, and then rule high entropy. The condition should be something like this: for I in 0 to P dot number, sorry, P dot number of sections -1. We are trying to look at every section, and this is the syntax to do it. We want to have math dot entropy receiving the PE dot sections index I dot raw data offset, and also the PE dot sections I dot raw data size. So we want to calculate the entropy of this, and we want the entropy to be more than 7. Let's see if this works. Now we do YARA -R high entropy. Oops, sorry, yeah, wrong syntax. For any I in, so this should work. No. What is wrong here? On the math, entropy. Oops. Okay. So see, the rule doesn't give us any error, but we couldn't find anything in the exercises. Let me go one step back. I actually have here the exercises, some of the YARA rules that we have written, and I have the tools. You see here inside the tools, I have the tools that I shared with you, the AdLice PViewer setup, Explorer Suite, and so on. So if I run the YARA rule here, YARA rule is here. You can see that the high entropy rule has found this AdLice PViewer setup. Okay, any questions? Is it clear? I hope it's not too fast. It's not a very sophisticated rule. I was just trying to show you something so you can use it later in your YARA rules, and I wanted you to have seen it at least once and know that it's quite easy to use. It's just a matter of using the correct imports and using the correct syntax. As you see, we have failed with the syntax a few times because I was in a rush to make sure that that we are not running out of time. So we are almost done here. This was the last exercise. Okay, I have one bonus exercise. If you guys want, you can like take a screenshot or write this down. This is a fun practice you can try for yourself and see if you can write a YARA rule that catches something like this. If you start trying, you will figure out that it's a bit tricky. I'll explain the exercise to you. So what we want here is to write a YARA rule to catch HTML files with injected scripts at the end of the files. It's common in some script injectors to inject a script tag at the end of the HTML file. So in normal cases, it's not usual to have a script tag after the HTML tag ends, right? But in some malicious injections, you can see something like this. So what we want to do is to write a YARA rule that catches this. But the challenging part is that if you look at this specific strings like the HTML open and close tags and script open and close tags and um, try to make the rule look for script tags after the end of HTML tags, it might not work because in many cases there are script tags already inside the HTML code, and with the at variable, you only get access to the first occurrence of each string. So your YARA rule might catch this one and this one, and because the offset is lower than the offset of the HTML file, you may lose and miss this file. So this is just a fun exercise for you to work on it. We are done. If you have any questions, let me know. If not, if you have any suggestions, I'm happy to hear if something was not clear. Happy to hear about that too.